All right, now we're going to look at two special cases of factoring. One is called the difference of two squares. So here's kind of our rule for the difference of two squares. If you have a perfect square in the front and a perfect square in the back and they're separated by a subtraction sign, that's when it's the difference of two perfect squares. And we'll always factor those the same way. It'll be when we'll have the square root of the first term, and one will have the square root of the last term, and then one will be a positive and one will be a negative. It doesn't matter which one's which, just like the order of the two binomials doesn't matter which way you write them, as long as you have one of each. So here's an actual example of a difference of two squares, where we'd have x squared minus 9. So x squared is obviously a perfect square. Its square root is just x. And 9 is a perfect square. Its square root is 3. So we are going to have an x in both places, a 3 in both places, and then one's positive and one's negative. Now let's see how that works. So if you were to FOIL this back out, we would have x times x, which is x squared, x times negative 3, which is negative 3x, 3 times x, which is positive 3x, and 3 times negative 3, which is negative 9. And so you can see that the middle terms will cancel out, and that's why we don't have a middle term for either one of these. Because we have one set that's positive and one set that's negative, that middle term will always cancel out. And that's when you know you have a difference of squares problem. Something else that I want to point out about this is always, our first rule is to always check for a GCF, a greatest common factor. So if we're looking at this example right here, 8 and 2 do have a greatest common factor. So before we do anything else, we're going to factor out that greatest common factor. So we pull out the 2, and what we're left with is 4x squared minus 2 divided by 2 is just 1. So we took out our GCF. Now when we look at what's left inside the parentheses, 4x squared is a perfect square because the square root of 4 is 2 and the square root of x squared is x. And 1 is a perfect square. The square root of 1 is just 1. So now we can set up our two parentheses. We said the square root of 4x squared was 2x. The square root of 1 is 1. Now 1 needs to be positive and 1 needs to be negative so that our middle terms will cancel out. And then we're still going to put our GCF out in front. All right, two more examples of that. So here we have 100 minus m squared. So it's still a difference, which is good. If there's ever a plus sign in between them, we can't factor those the same way. We would actually call that prime. It's not factorable. But we do have a difference, a subtraction sign. Square root of 100 is 10. Square root of m squared is just m. So we can set up our two parentheses. We have 10 and 10. Square root of m squared is m and m. M times m is m squared. And then 1 needs to be positive and 1 needs to be negative. And it doesn't matter which one comes first, the positive or the negative. Okay, one more example. The square root of 16h squared would be 4h. The square root of 49 is 7. So we'll set those up the same way. We have 4h and 4h, 7 and 7. 1 needs to be positive and 1 needs to be negative. And again, you can always check your work by FOILing it out and making sure that your middle terms cancel out and you get what you started with. The second type of special case we're going to look at are perfect square trinomials. So in our last case, we only had a binomial, but they were separated by a subtraction sign. Now we're going to look at trinomials that are perfect squares. So really, to ever check for these shortcuts, you would always just check your first term and the last term and see if both terms in the front and the back are perfect squares. If they're both perfect squares, check to see if it's either a difference of squares problem or a perfect square trinomial. So here's our rule. If we have a perfect square in the front and a perfect square in the back, and the middle term is 2 times a times b, then that means you have a perfect square trinomial that can, when you factor it, will look like this. Or if this is a subtraction sign right here, then this will be a subtraction sign right there. Now, it will never work if you have a subtraction sign in the back because you can never take the same number twice to get a negative number in the back. So let's look at a real example of what that might look like. So if I look in the front of this trinomial, I get n squared, which we know the square root of n squared is n. And the back is a perfect square. The square root of 16 is 4. So if I were to look at this, I would say, okay, there's a plus sign right there. So we know it's going to be plus. Then square root of n squared is n. Square root of 16 is 4. Now we got to check. Is 2 times 4 times n 8n? And it is. So this would be n plus 4 squared. Now you can always factor these the old-fashioned way, and you would get plus sign in the back means they're going to be the same sign. They're both going to be positive. Two numbers that multiply to get 16 and add to 8 are 4 and 4. So we get the same thing either way you do it, but there are some advantages to checking for a shortcut, and we'll get to some of that in just a minute. All right, let's look at a couple more examples of perfect square trinomials. And I've kind of been cheating a little bit. I keep forgetting to ask, what's the GCF? So in this first example, if we see 4, 12, and 9, there is not a GCF there. But 4 is a perfect square and 9 is a perfect square. So let's see if it makes a perfect square trinomial. So the square root of 4x squared is 2x. The square root of 9 is 3. There's going to be a minus sign in between, so it would be 2x minus 3 times 2x minus 3 if we factored it out. But we have to check to make sure it works. So to check, you take 2 times the back times the front. So 2 times negative 3 times 2. And we do get negative 12. So this would be a perfect square trinomial, and 2x minus 3 squared would be your answer. All right, now looking at this last example, in the front, we do have a perfect square in the front. It would be 3z, and we do have a perfect square in the back, which is 6, but we always have to check for a greatest common factor. It's wrong if you don't pull out a greatest common factor first, so make sure you check for that before you check for anything else. And we do have a greatest common factor here, it's 9. So even though we had a perfect square in the front and the back, if there is a GCF, you do have to factor that out first. So when we factor out our 9, we get z squared plus 4z plus 4. And we're still left with a perfect square trinomial when we're done. The square root of z squared is z. The square root of 4 is 2. But this is a pretty easy one to factor on your own if you wanted to just do it the long way. Right, we have a plus and a plus. Two numbers that multiply to get 4 and add to 4, that's 2 and 2. So you could write your answer like that, or you could write it 9 times z plus 2 squared. That's all.